Welcome. I'm so glad you're joining us for this deep dive today.
Yeah, thanks for having me. And thanks to all of you for being here.
Because today we are taking on something absolutely massive.
Massive is definitely the right word for it.
Right. I mean that literally and figuratively. We've got this dense, incredibly comprehensive report sitting right in front of us. It's simply titled Big Ideas in Physics.
Just a small, casual topic.
Yeah, exactly. Just the fundamental rules of reality. But our mission today is to extract the ultimate shortcut for you. We're going to distill these rules that govern everything.
So you can walk away from this feeling completely well-informed about, well, the architecture of the universe itself.
It's quite the mission.
It really is. The source material we're working with, it's essentially a grand tour of 10 monumental concepts.
10 massive paradigm shifts.
Right. We're charting a course from the bedrock of classical mechanics, stepping into the absolute bizarre, counterintuitive realm of quantum mechanics, and stretching all the way out to the very edges of the cosmos with modern cosmology.
But the goal here isn't just to list a bunch of laws like we're reading a textbook.
No, not at all. Our goal is to understand exactly why these ideas matter. We want to look at how each era of discovery totally shattered the previous paradigm.
And most importantly, how these fundamental rules shape your everyday life in ways you probably don't even realize.
Exactly.
And I want to promise you right now, there is going to be no overwhelming jargon today.
Or at least, if we do hit some jargon, we're going to translate it immediately.
Yeah, we're hunting for those aha moments, the times when the underlying code of reality suddenly just snaps into focus. Okay, let's unpack this. To really understand where physics is going, we have to start with the foundational block.
The rules of the everyday.
Right, and that means we have to talk about Sir Isaac Newton and his 1687 masterwork, the Principia Mathematica.
Which is arguably the most important book ever written in human history.
I don't think that's an overstatement.
It's really not. But to genuinely appreciate the magnitude of what Newton achieved, we have to understand the intellectual suffocating grip of the worldview he destroyed.
What people believed before him.
Right. Before Newton, the prevailing view of the physical world was still heavily dictated by Aristotle.
And Aristotle's physics were completely different from how we think today.
Entirely. Aristotelian physics was built on teleology.
Which is the idea that objects have a purpose, right?
Yeah.
Or a natural desire.
Exactly. Like the idea that a rock falls to the ground because it wants to return to the earth.
Well, smoke rises because it wants to return to the heavens.
Yes, it ascribed almost psychological motives to inanimate objects.
Which is so wild to think about now.
It really is. And Aristotle also believed that the natural state of any object on Earth was to be at rest.
Right.
If you wanted something to keep moving, you had to keep pushing it. Which, it made intuitive sense to people at the time.
Sure, if you stop pushing a wooden cart on a dirt road, it stops.
Right. But Newton, building on the brilliant, deeply subversive insights of Galilei and René Descartes, realized that the stopping wasn't a natural state of rest.
The stopping was an illusion.
An illusion created by an invisible force, friction.
So Newton strips away the purpose and the desire of objects, and he replaces it with cold, hard determinism.
And this is his first law, the law of inertia.
Which sounds so simple to us today. An object in motion stays in motion. An object at rest stays at rest, unless acted upon by a force.
But historically, it was a philosophical earthquake.
He was saying that moving at a constant velocity is fundamentally indistinguishable from standing still.
Right. If you are floating in the deep vacuum of space, moving at 10,000 miles an hour, you feel absolutely nothing.
You feel like you're at rest.
Exactly. And that leads directly to the core engine of Newtonian physics, the second law.
The famous equation, force equals mass times acceleration, F equals m times a.
But let's look at what that equation is actually saying. It is a predictive machine.
A predictive machine.
Yeah. It says that if you know the mass of an object and you know the total forces acting upon it, you can calculate exactly how its motion will change. You can predict its future.
It's the math that governs essentially all of our macro-level engineering. Like when automotive engineers are designing the brakes on a car, they are just playing with the variables of F equals ma.
Right. How much force is required to decelerate a 2-ton mass before it hits a wall?
Exactly. And then you have the third law. For every action, there is an equal and opposite reaction.
Which is really a profound statement about the symmetry of nature. Forces do not exist in isolation.
There are always interactions between two things.
Always. If a rocket is in the vacuum of space, There's no air for it to push against to move forward.
And the intuition of the time said space travel was impossible for that very reason.
Right, what are you pushing off of?
Hmm.
But Newton's third law reveals the workaround. The rocket pushes superheated exhaust gases backward with tremendous force.
And the exact equal and opposite reaction is those gases pushing the rocket forward.
Exactly. So Newton creates this beautifully coherent, deterministic, clockwork universe. He proves that the exact same mathematics governing an apple falling from a tree in an orchard in England.
Also governs the moon orbiting the Earth.
Yes, he united the heavens and the earth under one set of rules, and that framework went practically unchallenged for over 200 years.
But classical physics isn't just about motion, is it? It's also about accounting.
Right. We have to look at the conservation laws.
Because the universe is an incredibly strict auditor. It simply does not allow you to get something from nothing.
The big three here are the conservation of energy, the conservation of momentum, and the conservation of mass.
Let's ground this for you. Take a roller coaster. When the motor drags the cars up to the highest peak, it is storing a massive amount of potential energy.
Right.
When it drops, it doesn't create new energy to accelerate. It simply trades that stored potential energy into kinetic energy.
The total ledger remains balanced.
And momentum conservation is the entire basis of accident reconstruction. If two cars collide, the total mass times velocity before the crash must perfectly equal the mass times velocity of the wreckage skidding away.
And the historical formulation of these laws took centuries of meticulous, often tedious work. Antoine Lavoisier in the late 1700s is a great example.
What did he do?
Well, before him, people thought burning wood meant matter was being destroyed, leaving only lightweight ash.
Which makes sense if you just look at it.
Right. But Lavoisier sealed chemical reactions inside glass containers, burned them, and weighed the whole apparatus before and after.
And the weight never changed.
It never changed. He proved that the mass of the wood didn't vanish. It just transformed into gases.
But seeing that the universe keeps a balanced ledger is one thing. Understanding why it keeps a balanced ledger is entirely different.
Oh, absolutely.
And this leads us to one of the most underrated, awe-inspiring moments in the history of science. We had to jump forward a bit to 1918 and talk about a mathematician named Emmy Noether.
Emmy Noether is a giant. Albert Einstein called her the most significant creative mathematical genius since the higher education of women began.
That is massive praise.
It was well-deserved. She formulated a theorem that is, without exaggeration, the bedrock of modern theoretical physics.
Noether's theorem.
Yes. She proved mathematically that every single conservation law is directly linked to a fundamental underlying symmetry of nature.
I really want to make sure we don't rush past this because it is staggering. When we say symmetry in this context, we aren't talking about a butterfly's wings. What exactly did Noether mean?
Think about time. We operate under the assumption that the laws of physics do not change depending on what day it is.
Right.
An experiment you perform on a Tuesday will yield the exact same result if you perform it on a Friday. The physics are symmetric or invariant across time.
We call this time translation symmetry.
Exactly. Noether proved, using deeply complex calculus, that because time translation symmetry exists, the conservation of energy must exist.
So conservation of energy isn't just an arbitrary rule.
No, it is the mathematical consequence of a universe where physics doesn't change over time.
And the same goes for space. Because the laws of physics are the same here on Earth as they are in the Andromeda Galaxy, which is space translation symmetry, the universe is forced to conserve momentum.
The laws of physics aren't just arbitrary decrees. They are reflections of the fundamental geometry and shape of reality itself.
It is an incredibly elegant, almost poetic realization.
It really is. But that elegance starts to get very messy very quickly when we move from the pristine orbits of planets to the chaotic reality of the Industrial Revolution.
Right. The universe might be elegant, but humans were suddenly building massive, loud, coal-burning steam engines.
And the industrialists of the 19th century didn't care about the poetry of the cosmos.
They cared about efficiency.
They wanted to know how to get more work out of less coal. And that purely practical engineering problem birthed thermodynamics.
Specifically, it birthed the first two laws of thermodynamics.
Right. The first law is essentially just an extension of energy conservation. It states that the change in a system's internal energy is equal to the heat added to the system minus the work done by the system.
It's strict thermal accounting.
But the second law is where our understanding of the universe takes a dark, irreversible turn.
The second law introduces entropy,
Yes.
the principle that in any closed system, disorder will naturally tend to increase. Heat will always flow from a hot object to a cold object. It will never, ever spontaneously flow the other way.
This is what physicist Arthur Eddington later called the arrow of time.
Because Newton's equations are time reversible, right?
Exactly. If you watch a video of two billiard balls bouncing off each other, and you play the video in reverse, it looks perfectly natural. The math works both ways.
But thermodynamics introduces a one-way street.
You can drop a coffee mug on the floor and watch it shatter. But you will never, in a trillion years, see those ceramic shards spontaneously reassemble themselves and jump back up onto the table.
Or, to use a chemical example, you pour cream into your dark roast coffee. It swirls and mixes perfectly. But you could stir that coffee for the rest of eternity, and the cream will never spontaneously unmix itself from the water.
The term entropy was coined by Rudolf Clausius in 1865, meaning transformation.
But it was the Austrian physicist Ludwig Boltzmann in the 1870s who really pulled back the curtain on why entropy happens.
He formulated a statistical definition of entropy, which is actually carved onto his tombstone. S equals KB times the natural log of W.
Okay, let's translate the math here. What was Boltzmann actually saying about the cream in the coffee?
He was saying that there is no magical physical force driving the cream to mix. It's purely a matter of overwhelming probability.
Okay.
Think of all the microscopic arrangements of the molecules in your coffee cup. There are only a very tiny number of arrangements where all the cream molecules are huddled on the left side and all the coffee molecules are on the right. But there are billions, trillions of arrangements where they are mixed together. So as the molecules randomly bump around, they simply naturally wander into the most probable states.
Disorder isn't a force. It's just statistically inevitable.
Precisely.
And the cosmic implication of this is terrifying, because if the entropy of the entire universe is constantly increasing, energy is constantly spreading out, then eventually, way down the line, we hit the ultimate endpoint.
The heat death of the universe.
A state of maximum entropy where all the heat is completely evenly distributed, no energy flows, no stars can form, no work can be done, and the universe just freezes in a state of static perfection.
It's a bleak cosmological forecast, for sure.
Very bleak.
But while thermodynamicists were grappling with the eventual death of the universe, another massive, entirely separate puzzle was unfolding regarding electricity and magnetism.
Right. For a long time, these seemed like completely unrelated phenomena. You had static electricity from rubbing amber, and you had lodestones that magically attracted iron.
But then, in 1820, Hans Christian Ørsted is doing a lecture, and he notices that when he turns on a simple electric battery, a magnetic compass needle sitting nearby suddenly twitches.
And shortly after, Michael Faraday, a brilliant experimentalist with virtually no formal mathematical training, discovers the reverse.
He realizes that if you take a magnet and physically move it back and forth through a coil of copper wire, it pushes the electrons around. It induces an electric current.
So electricity can create magnetism, and changing magnetism can create electricity.
They were locked in a dance, but no one had the mathematical language to describe the choreography.
Enter James Clerk Maxwell in the 1860s. He takes Faraday's intuitive sketches of magnetic lines of force and translates them into rigorous mathematics.
He synthesizes all the previous work into a set of 4 elegant equations.
But the sources note that Maxwell had to add a completely new hypothetical concept to make the math work, something called the displacement current.
Right.
Why did he need to do that? What exactly was being displaced?
That is the genius of Maxwell. Faraday showed that a changing magnetic field creates an electric field. But Maxwell's equations demanded symmetry.
There's that word again, symmetry.
He realized that a changing electric field must also create a magnetic field, even if there are no wires, no moving electrons, just empty space.
He called this the displacement current.
Yes. It meant that an oscillating electric field could create an oscillating magnetic field, which would in turn create an oscillating electric field, and so on.
They could leapfrog off each other.
Self-propagating through the absolute vacuum of space.
They could form a wave. And when Maxwell calculated the speed at which this self-sustaining electromagnetic wave would ripple through space, the math spit out a very specific number.
Roughly 3 times 10 to the 8th meters per second.
Which astonishingly was already a famous number. It perfectly matched the measured speed of light.
In one of the greatest eureka moments in the history of human thought, Maxwell realized that light itself is simply a wave of electromagnetism.
It is hard to overstate how the single unification changed the trajectory of the human species. Phenomena of electricity, magnetism, and visible light were all suddenly understood as the exact same thing, just vibrating at different frequencies.
Every time you heat up food in a microwave, or get an X-ray, or connect your phone to Wi-Fi, you are manipulating the exact fields Maxwell described.
But Maxwell's equations contained a hidden landmine that would soon blow up the entire foundation of classical physics.
Oh yeah, a big one.
His equations predicted that the speed of light denoted by the letter c is a fixed constant. It is baked into the very fabric of the electromagnetic fields.
But classical Newtonian physics said that speeds are relative.
Let's illustrate this contradiction for you. If I am standing on the bed of a pickup truck driving 50 miles an hour and I throw a baseball forward at 50 miles an hour, a person standing on the sidewalk sees that baseball traveling at 100 miles an hour.
The speeds add up. That's Newton.
So naturally, the physicists of the late 19th century assumed light must work the same way.
They also assumed that just like sound waves need air to travel through, light waves must travel through an invisible stationary medium filling the universe, which they called the luminiferous ether.
Which brings us to 1887 and the famous Michelson-Morley experiment.
Right, they built an incredibly sensitive apparatus called an interferometer, floating on a pool of liquid mercury in a basement in Ohio to eliminate vibrations.
The goal was to split a beam of light, send it in two different directions, and bounce it back. Since the Earth is hurling through space at 67,000 miles an hour, it should be crashing through this ether.
Right, it's like swimming upstream in a river versus swimming across the river. The light beam traveling parallel to the Earth's motion should take slightly longer to return than the beam traveling perpendicular to it.
Exactly. But they ran the experiment and they found nothing. A complete monumental null result.
The light beams returned at the exact same instant, every single time, no matter which way the apparatus was pointed or what time of year it was.
The speed of light did not change. The ether did not exist.
This sent the scientific community into an absolute panic. The math of electromagnetism said light was constant. The math of Newton said speeds had to add up. Reality was contradicting itself.
And it took a 26-year-old patent clerk named Albert Einstein in 1905 to look at this contradiction and say, what if the universe isn't broken? What if Maxwell is right and Newton is wrong?
Einstein formulated a special theory of relativity based on one radical postulate. The speed of light in a vacuum is the absolute same for all observers, regardless of how fast they are moving.
If you are flying in a spaceship at 99% the speed of light and you shine a flashlight forward, the light beam doesn't leave you at 1% the speed of light.
It races away from you at the exact same constant speed, see?
But if you make the speed of light the absolute rigid yardstick of the universe, the mathematics demand that something else has to give.
And what gives, Einstein realized, is our shared experience of space and time.
This is where we get the mind-bending consequences of special relativity. Because the speed of light is distance divided by time, if the speed must remain constant for two observers moving at different relative speeds, then their measurements of distance and time must disagree.
This means time dilation.
If I put you in a rocket ship and launch you close to the speed of light, your biological clock, your mechanical watch, the very vibration of your atoms slows down relative to me standing on Earth.
You are literally traveling into the future.
It also means length contraction. As you approach the speed of light, your rocket physically compresses along the direction of motion from my perspective.
And of course, the culmination of special relativity was the realization that mass and energy are not independent, conserved quantities.
They are two sides of the same coin, united by the equation E equals mc squared. Mass is simply heavily concentrated energy.
But Einstein knew special relativity had a massive flaw. The word special meant it only applied to special cases, objects moving at a constant, steady velocity.
It completely ignored acceleration, and more importantly, it ignored gravity.
Newton said gravity was an instantaneous, invisible tether, pulling objects together across space. But Einstein's new speed limit of the universe said nothing, not even gravity, can travel faster than light.
So Einstein spends the next 10 years, from 1905 to 1915, locked in an intense mathematical struggle to rewrite gravity.
His guiding light was a thought experiment he called his happiest thought, the equivalence principle.
He realized that if you are in a windowless elevator accelerating upward through deep space at 9.8 meters per second squared, the floor pushing up against your feet feels exactly, indistinguishably the same as standing still on the surface of the Earth feeling the pull of gravity.
Acceleration and gravity are essentially the same physical phenomenon. And from that leap, Einstein develops general relativity.
He throws out Newton's invisible tether entirely.
He says gravity isn't a pulling force. Gravity is the geometry of the universe itself. It is the curvature of space-time.
The classic analogy is a heavy bowling ball sitting in the middle of a stretched rubber trampoline. The trampoline sags and curves around the ball.
If you roll a small marble straight across the edge of the trampoline, its path will curve inward toward the bowling ball.
The bowling ball isn't exerting a magnetic pull on the marble. It has simply warped the physical space that the marble is traveling through.
As the physicist John Wheeler beautifully summarized it, matter tells space-time how to curve, and space-time tells matter how to move.
It's an unbelievably bold claim to say that the empty space between the planets isn't empty, but is actually a malleable, warping fabric, and he needed proof.
So in 1919, the British astronomer Arthur Eddington organizes an expedition to the island of Principe off the coast of Africa to view a total solar eclipse.
The goal was to look at the light from distant stars in the Taurus constellation as that light passed right behind the edge of the darkened sun.
According to Newton's equations, the starlight should bend slightly just due to the sun's sheer mass.
But according to the new radical math of general relativity, the sun's massive dent in the trampoline of space-time should bend the starlight exactly twice as much.
The eclipse happens. The photographs are taken and meticulously analyzed.
And Einstein is right. The starlight bent exactly as general relativity predicted. The fabric of reality was curved. Einstein became a global icon overnight.
But I know what you might be thinking. Bending starlight during an eclipse is fascinating. But what does curved space-time have to do with you? How does it affect your life today?
The most visceral, everyday application of general and special relativity is sitting in your pocket. The Global Positioning System.
GPS relies on a constellation of satellites orbiting the Earth, broadcasting incredibly precise atomic time signals to your phone.
Your phone calculates the time delay from multiple satellites to triangulate your exact position on the globe.
But those satellites are moving at roughly 14,000 kilometers per hour.
According to special relativity, because they are moving so fast relative to us on the ground, their atomic clocks actually tick slower by about 7 microseconds a day.
And it gets more complicated. Because those satellites are 20,000 kilometers above the Earth, they are further away from the center of Earth's mass.
They are sitting in a weaker gravitational field.
And general relativity dictates that time actually runs faster in winter gravity. This effect speeds up the satellite clocks by about 45 microseconds a day.
So you have a net difference. The clocks speed up by 45 microseconds due to gravity and slow down by 7 microseconds due to speed. That leaves a net error of 38 microseconds a day.
Now, 38 microseconds sounds completely negligible, but light travels fast.
If the engineers who built the GPS system did not actively program the satellite software to correct for Einstein's theories, the navigational fix would drift by roughly 10 kilometers every single day.
Within a week, your phone's map would think you were in a different city.
It is a stunning validation of the theory. The engineers literally had to build a relativistic correction switch into the early satellites just in case Einstein was wrong and the clocks ticked normally.
But he wasn't. Our modern navigational grid only functions because we mathematically compensate for the fact that time is bendable.
General relativity didn't just give us GPS. It unlocked the extreme cosmos. It gave us the mathematical framework to understand black holes' regions where matter collapses so densely that the curvature of space-time becomes infinite.
An event horizon from which not even light can escape.
It predicted gravitational lensing, where entire galaxies act as magnifying glasses for the light behind them.
And we can't forget 2015, the monumental achievement of the LIGO observatories. They detected literal ripples in the fabric of space-time gravitational waves caused by the collision of two black holes over 1 billion light-years away.
They measured a stretching and squeezing of space that was thousands of times smaller than a single proton.
It was the ultimate proof of what Einstein's old math professor Hermann Minkowski realized back in 1908. Space and time are not independent stages. They are fused into a single four-dimensional continuum.
Space-time. So Einstein creates this perfectly smooth, geometric, deterministic map of the cosmos. But ironically, at the exact same time he was doing that, he helped kick off a completely different scientific revolution that would ultimately ruin that deterministic view forever.
We have to shrink down from the macro universe to the subatomic world, the microscopic casino of quantum mechanics.
The transition from classical physics to quantum mechanics is fundamentally a story of classical physics failing.
In the late 19th and early 20th centuries, physicists were dealing with something called the ultraviolet catastrophe,
Classical equations predicted that a perfect heat radiator, a black body, should emit an infinite amount of high-frequency ultraviolet radiation.
which is obviously impossible, or opening an oven door would vaporize you.
To fix the math, Max Planck in 1900 proposed what he thought was just a desperate mathematical hack. He suggested that maybe electromagnetic energy doesn't flow in a continuous smooth wave like water from a hose.
What if it is only emitted in discrete, indivisible packets, or quanta, like bullets from a machine gun?
Planck didn't fully believe his own math represented reality. But in 1905, the exact same year he published Special Relativity, Einstein took Planck's idea literally.
He used the quantum concept to explain the photoelectric effect, proving that light is actually composed of individual particles, which we now call photons.
Then Niels Bohr took the quantum baton and applied it to atoms, showing that electrons can't just orbit a nucleus wherever they want.
They are locked into specific quantized energy levels. They literally teleport from one orbit to another without existing in the space between. A quantum leap.
And then Louis de Broglie flips the script entirely. He says, okay, if light, which we thought was a wave, can act like a particle, then maybe solid matter, which we know are particles, can act like a wave.
And this sets the stage for what has to be the most mind-shattering experiment in all of physics, the double-slit experiment.
It is the experiment that forces us to abandon our intuitive understanding of reality. Let's walk through it carefully.
Imagine you have a barrier with two tiny vertical slits in it and a photographic screen behind it. If you shine a laser beam, a wave of light at the barrier, the wave goes through both slits, split into two new waves, and they overlap.
Where the crests of the waves meet, they amplify. Where a crest meets a trough, they cancel each other out. You get a classic interference pattern on the back screen, a barcode of bright and dark stripes.
That makes total sense for a wave. Water ripples do the exact same thing. But then experimentalists decided to do the exact same setup using solid matter.
They fired single solid electrons one by one like tiny bullets toward the two slits. Now, classical logic dictates that a solid bullet has to go through either the left slit or the right slit.
You should just get two simple bands of impacts on the back wall.
But that is not what happens. Even when you fire the electrons one at a time with long pauses in between, they do not form two bands.
Over time, the individual impact dots slowly build up the exact same barcode interference pattern.
Stop and think about how insane that is. A single solid electron is fired. It somehow goes through the left slit and the right slit and neither slit and both slits all at the same time.
It acts as a wave of probability, passes through the barrier, interferes with itself, and then right before it hits the back wall, it decides to collapse back into a solid particle to make a single dot.
The physicists were understandably bewildered, so they decided to cheat.
They set up a microscopic detector right at the slits to measure definitively which slit the electron actually passes through. They want to catch the electron in the act.
And this is where physics feels like magic. The moment you turn on the detector to measure the electron's path, the interference pattern on the back wall completely vanishes.
The electrons go back to acting like normal bullets, creating two simple lines.
So the very act of observing the particle forces it to choose a path. The universe literally changes its behavior depending on whether or not we are looking at it.
It is deeply unsettling. Erwin Schrödinger developed the wave equation to describe this behavior, but it doesn't describe the physical location of the electron.
As Max Born realized, Schrödinger's wave is a wave of pure probability.
Until an electron is measured, it exists in a state of superposition, meaning it is essentially occupying all possible states and locations at once, weighted by probabilities.
This is where Schrödinger's famous cat thought experiment comes from. He was trying to highlight how absurd this all is.
If you put a cat in a box with a radioactive atom that has a 50-50 chance of decaying and releasing a poison gas, the math of quantum mechanics says that before you open the box to check, the atom is both decayed and not decayed.
Therefore, the cat is in a macroscopic superposition of being simultaneously alive and dead.
And you combine this with Werner Heisenberg's uncertainty principle. Heisenberg proved mathematically that you cannot know both the exact position and the exact momentum of a particle at the same time.
The more precisely you measure where a particle is, the less you can possibly know about where it is going.
It's not a flaw in our microscopes. It is a fundamental fuzziness built into the fabric of reality.
Einstein absolutely hated this. He famously declared, "God does not play dice with the universe."
He believed in the deterministic clockwork. If you have probability, Einstein thought, it just means you are missing some hidden variables.
He and his colleagues formulated the EPR paradox to try and break quantum mechanics. They pointed out that if quantum mechanics is true, you could have two particles become entangled.
Meaning their properties are linked. If you measure one particle here on Earth, it instantly forces the other particle to snap out of superposition, even if that second particle is on the other side of the galaxy.
Einstein called it spooky action at a distance and said it violated the speed of light.
Einstein went to his grave believing quantum mechanics was an incomplete theory. But decades later, physicist John Bell formulated a mathematical theorem to test Einstein's hidden variables idea.
And the subsequent experiments proved Einstein wrong. There are no hidden classical variables pulling the strings. The universe at the subatomic level really is a probabilistic non-local casino.
And what's wild is that this seemingly philosophical weirdness is the foundation of our entire modern technological civilization.
We aren't just philosophizing about probability waves, we are engineering them. Our entire understanding of chemistry, how atoms bond to form molecules, is purely quantum mechanics.
The way electrons tunnel through silicon barriers is the basis of every semiconductor and microprocessor on Earth.
Without the weirdness of quantum mechanics, you have no internet, no smartphones, no MRI machines, no lasers.
This deep understanding of the quantum realm culminated in what is arguably the most successful scientific theory ever constructed: the Standard Model of particle physics.
If the periodic table of elements organizes all the different types of atoms, the Standard Model organizes the fundamental, indivisible building blocks that make up those atoms.
It says that everything in the known universe, excluding gravity, is constructed from just 17 fundamental particles.
Instead of just listing them off, let's look at how they are categorized. The Standard Model divides reality into two camps: the matter particles and the force carriers.
Exactly. The matter particles are called fermions. There are 12 of them. 6 are quarks, which have whimsical names like up, down, charm, strange, top, and bottom.
Quarks bind together tightly to form the protons and neutrons inside the nucleus of an atom.
Then you have 6 leptons. The most famous lepton is the electron, which orbits the nucleus. The others are the heavier muon and tau particles, and 3 ghost-like particles called neutrinos,
which are so light and interact so weakly that trillions of them are passing through your body right now without you feeling a thing.
So those 12 fermions are the bricks. But bricks need mortar to hold a building together, and that's where the bosons come in. Bosons are the force-carrying particles.
Whenever matter interacts, it is essentially passing bosons back and forth.
If two magnets repel each other, they are exchanging photons, the boson of the electromagnetic force.
Inside the nucleus of the atom, the protons are all positively charged. They should repel each other and blow the atom apart.
But they are held together by gluons, the bosons that carry the strong nuclear force. And then you have the W and Z bosons, which carry the weak nuclear force, responsible for radioactive decay and the nuclear fusion that powers the sun.
But the Standard Model is more than just a list of ingredients. The sources highlight that it is built on deeply complex mathematical symmetries, referred to as SU3 cross, SU2 cross U1. What exactly does that alphabet soup mean?
It relates back to what we discussed with Emmy Noether. Those letters and numbers represent gauge symmetries.
Think of a perfect sphere. If you rotate a sphere 90 degrees, it looks exactly the same. It is symmetric under physical rotation.
The symmetries of the Standard Model are abstract internal mathematical rotations. Physicists discovered that if you force the equations of quantum mechanics to remain perfectly symmetric under these complex internal transformations, the math automatically dictates the existence of the force-carrying bosons.
The forces of nature are literally just the mathematical consequence of the universe demanding symmetry.
That is beautiful. But the theory had one massive glaring hole for decades. The math of these perfect symmetries dictated that all these particles should be massless. They should all zip around at the speed of light.
But we know an electron has mass. We know a top quark has mass. So how do they get it?
That was the puzzle Peter Higgs and others solved in the 1960s, leading to the 17th and final particle of the model, the Higgs boson.
They proposed that the entire universe is filled with an invisible, energy-dense field, now called the Higgs field. You can think of it like a cosmic vat of molasses.
As particles travel through space, they interact with this field. A photon slips through the molasses effortlessly. It interacts with nothing, so it has zero mass and travels at the speed of light.
But an electron drags through the molasses. That resistance, that drag, is what we experience as mass.
And it took a 17-mile-long underground ring of superconducting magnets, the Large Hadron Collider in Geneva, smashing protons together at near the speed of light to finally knock a piece of that molasses loose and detect the Higgs boson in 2012.
It was a triumph of theoretical prediction.
The Standard Model's predictive power is unmatched. It predicted the existence of the W and Z bosons, the top quark, and the Higgs, decades before we had the technology to find them.
And yet, despite all of its incredible success, the Standard Model is ultimately a broken map because, as we mentioned earlier, it completely ignores gravity.
Gravity is simply too weak at the microscopic scale to fit into the quantum equations. And as we zoom out from the subatomic world to the grand cosmic view, we realize just how much the Standard Model is missing.
This is where we transition to modern cosmology. We are moving from the incredibly small to the unimaginably vast. And to understand the cosmos, we have to start at the absolute beginning, the Big Bang.
The history of how we discovered the Big Bang is fascinating, because Einstein originally missed it.
His equations of general relativity suggested the universe should be collapsing under its own gravity. To fix this, he added a fudge factor, the cosmological constant, to force the universe to remain static and eternal.
But in the 1920s, a Belgian priest and physicist named Georges Lemaitre looked at the pure math and said, no, the universe is expanding. And if it's expanding today, it must have been smaller yesterday. Ergo, it must have begun from a single, infinitely dense, primeval atom.
Einstein initially dismissed Lemaitre, but then Edwin Hubble pointed the massive Hooker telescope at Mount Wilson toward distant galaxies.
By analyzing the light from these galaxies, Hubble noticed they were all redshifted, meaning the light waves were being stretched out.
The only way that happens is if the galaxies are moving away from us, and the further away they were, the faster they were receding.
Lemaitre was right. The fabric of space itself was stretching.
The definitive proof came in 1965, and it was a complete accident. Arno Penzias and Robert Wilson were working at Bell Labs using a massive, horn-shaped radio antenna to study satellite communications.
But they kept picking up this persistent, irritating microwave hiss.
They pointed the antenna at New York City, assuming it was urban interference. They even climbed into the antenna and meticulously scraped out pigeon droppings, thinking that was causing a malfunction.
But the hiss wouldn't go away. It was uniform, coming from every direction in the sky, day and night.
They had accidentally tuned into the oldest broadcast in existence. They had discovered the cosmic microwave background, the CMB.
It is the literal cooled-down afterglow of the Big Bang itself. About 380,000 years after the initial expansion, the universe cooled enough for the first atoms to form, releasing a flash of light that has been stretching into microwaves for 13.8 billion years.
So we have this beautiful cosmological timeline, the Big Bang, the CMB, the first stars igniting, galaxies coalescing. But as astronomers got better at observing the cosmos, they realized the math wasn't adding up.
The gravity we could see wasn't enough to explain the motion we were observing. And this leads us to the most humbling statistic in all of science.
Every single thing we have discussed today, every quark, every electron, the Higgs boson, the planet Earth, the sun, all the billions of stars in the Andromeda galaxy.
All of that normal visible matter accounts for just 5% of the total mass energy content of the universe. The other 95% is completely invisible to our entire Standard Model.
Let's break down that dark 95%. About 27% of the universe is dark matter. And we have to give credit to Vera Rubin in the 1970s. She was studying spiral galaxies, meticulously tracking the rotational speeds of stars.
Based on Newtonian physics and general relativity, the stars on the outer rim of a galaxy should orbit much slower than the stars near the dense, bright center, just like Pluto orbits the sun much slower than Mercury.
But Rubin found that the outer stars were moving astonishingly fast. So fast, in fact, that the visible mass of the galaxy did not possess enough gravity to hold them in.
They should have been flung out into deep space like a child letting go of a merry-go-round.
The only way the math holds together is if the visible galaxy is actually embedded inside a colossal invisible halo of mass. This is dark matter.
It doesn't emit light, doesn't reflect light, it doesn't interact with electromagnetism at all. It acts purely as a gravitational glue.
And we see it everywhere now, not just in rotation curves, but in gravitational lensing, where huge, invisible blobs of dark matter warp the light of galaxies far behind them.
So dark matter pulls things together. But the remaining 68% of the universe does the exact opposite.
In 1998, two independent teams of astronomers were looking at Type Ia supernovae exploding stars that act as standard cosmic light bulbs in very distant galaxies.
The goal was to measure the deceleration of the universe. Because naturally, the collective gravity of all the matter and dark matter should be pulling the universe inward, slowing down the expansion from the Big Bang.
But they found the exact opposite. The distant supernovae were much dimmer than expected, meaning they were much further away than the models predicted.
The expansion of the universe isn't slowing down, it is actively accelerating.
And the mechanism driving this acceleration is what we call dark energy. It acts as a repulsive, anti-gravity force inherent to the vacuum of space itself.
The more space expands, the more dark energy there is to push it apart faster. Ironically, this looks exactly like the cosmological constant, the fudge factor Einstein introduced and later called his biggest blunder.
It turns out, empty space isn't empty. It exerts a negative pressure pushing the galaxies apart.
This totally rewrites the fate of the universe. If dark energy continues to dominate, we are heading for the big freeze.
The galaxies will be pushed so far apart that their light can never reach us. The night sky will go completely black.
The stars will eventually burn through their nuclear fuel, the black holes will evaporate via Hawking radiation, and the universe will just be a cold, endlessly expanding void approaching absolute zero, maximum entropy.
It is a profound, if chilling, cosmic destiny. But before physicists worry about the end of time, they have an agonizing crisis right here in the present. And this brings us to the final frontier of the source material, the ultimate unification, the quest for a theory of everything.
We have spent this deep dive looking at two incredibly successful pillars of physics. General relativity gives us a smooth, continuous, geometric description of gravity and the macro universe.
Quantum mechanics gives us a jittery, discrete, probabilistic description of the other three forces and the microuniverse.
They both work perfectly in their respective domains. So what is the problem? Why can't we just use both?
Because eventually the domains overlap. If you want to understand the exact center of a black hole, the singularity, or if you want to understand the exact moment of the Big Bang, you are dealing with something that is incredibly massive but also infinitesimally small.
And when you try to combine the mathematics of a smooth geometry with the mathematics of jittery quantum uncertainty, the equations literally explode. They spit out nonsensical infinities.
The two most successful theories in human history are mathematically incompatible.
Physicists have tried to build grand unified theories, or GUTs, to unite these strong, weak, and electromagnetic forces. But GUTs usually predict things we've never seen, like protons spontaneously decaying.
And more importantly, GUTs completely ignore gravity. To truly unify physics, we need a theory of quantum gravity. We need a way to force gravity to play by quantum rules without the math breaking down.
And the most famous, heavily funded attempt at this is string theory.
String theory is a breathtakingly ambitious mathematical framework. It proposes that our fundamental premise is wrong. The Standard Model treats electrons and quarks as zero-dimensional points.
String theory says, what if we zoom in a billion times closer? Those points are not dots. They are unimaginably tiny, one-dimensional closed loops or open snippets of vibrating energy. Strings.
Think of a violin string. Depending on how you pluck it, how much tension is on it, it vibrates at different harmonic frequencies to produce different musical notes.
String theory says the universe works exactly the same way. If a string vibrates one way, it manifests as an electron. If it vibrates another way, it manifests as an up quark.
The entire particle zoo of the Standard Model is just the cosmic symphony of these vibrating strings.
And here is the magic trick of string theory. When physicists ran the mathematics of these vibrating quantum strings, they found that one of the required vibrational states perfectly describes a massless particle with a quantum spin of 2.
In quantum mechanics, a massless spin 2 particle is the exact profile of the graviton, the hypothetical quantum particle that carries the force of gravity.
String theory didn't just accommodate gravity. It mathematically demanded it. It united gravity with the quantum world.
But the math of string theory comes with a massive counterintuitive catch. It doesn't work in our normal 3D reality.
To keep the math consistent and avoid those nasty infinities, the equations require the universe to have 10 or even 11 dimensions, as formulated in M-theory.
We experience 3 dimensions of space and 1 of time. So where are the other 6 or 7 spatial dimensions?
String theorists argue they are compactified. Imagine looking at a telephone wire from a mile away. It looks one-dimensional, just a line. But as you get closer, you see it has a circumference. An ant can crawl around it in a second dimension.
String theory posits that at every microscopic point in our 3D space, there are 6 extra dimensions curled up, or compactified, into complex geometric shapes, called Calabi-Yau manifolds, so small we can't perceive them.
And string theory also leads to mind-bending concepts like the holographic principle, specifically the ADE-CFT correspondence.
This is the mathematical discovery that a gravitational theory operating in a specific 3D volume of space can be perfectly translated into a quantum theory operating purely on the 2D boundary of that space.
It implies that our entire three-dimensional universe, including gravity, might just be a holographic projection of quantum information encoded on a distant 2D surface.
It is remarkably elegant, but string theory has fierce critics.
The primary criticism is that these strings are so incomprehensibly small, roughly the Planck length, which is 10 to the minus 35 meters, that we could never build a particle accelerator large enough to directly detect them.
It is criticized as being more philosophy and pure mathematics than empirical physics, which is why there is a major rival theory, loop quantum gravity.
If string theory tries to unify the particles, loop quantum gravity, or LQG, tries to unify the space.
Einstein taught us that space is a dynamic fabric, but he treated it as a continuous, smooth trampoline. LQG says, what if we apply quantum mechanics to the trampoline itself?
LQG proposes that space is not continuous. It is discrete. It is quantized. Just like a digital photograph looks like a smooth gradient from far away, but if you zoom in enough, you see it is made of individual, indivisible pixels.
LQG argues that the fabric of space is woven out of finite, discrete loops of gravitational field lines called spin networks.
The universe is pixelated. There's the smallest possible volume of space, and you cannot cut it in half.
And the incredible thing about pixelating space-time is that it naturally solves the problem of black holes and the Big Bang. In general relativity, a black hole collapses into a singularity, a point of infinite density and zero volume.
But in LQG, zero volume doesn't exist. Matter can only collapse down until it hits the fundamental pixel size of space, and then it can go no further. It prevents the infinities.
And this completely changes the origin story of the universe. Instead of a Big Bang springing from an infinitely dense singularity, loop quantum gravity suggests a big bounce.
An older, contracting universe collapsed, reached the maximum density allowed by the quantum pixels of space, and rebounded violently outward, creating the expansion we see today.
What an unbelievable journey this has been. We have taken a massive deep dive into the architecture of reality. We started with Newton tearing down Aristotelian purpose to give us deterministic clockwork.
We followed Maxwell as he realized light was just vibrating electromagnetism.
We rode along with Einstein as he destroyed absolute time, warping the very fabric of space-time to explain gravity.
We plunged into the terrifying probabilistic casino of quantum mechanics, where observation creates reality.
We mapped the 17 fundamental particles of the Standard Model, and then immediately humbled ourselves by realizing they only account for 5% of a dark, expanding cosmos.
And finally, we stood at the bleeding edge, hunting for 11-dimensional strings and pixelated loops of space.
It is a lot to process, but as we wrap up, I want to offer a final thought for you to carry with you. A natural consequence of everything we have discussed.
If you look at the trajectory of physics, from loop quantum gravity pixelating space, to the holographic principle suggesting our 3D world is a 2D projection, to quantum mechanics, proving that particles literally do not resolve their properties until they are observed, it leads to a very provocative modern theory.
The simulation hypothesis, the idea that reality isn't base reality.
Precisely. If space is fundamentally discrete and pixelated like a digital grid, if the maximum speed limit of the universe acts exactly like the processing speed limit of a computer processor, and if the universe only renders the specific details of matter when a conscious observer looks at it, saving rendering power just like a video game engine does, then the staggering complexity of the laws we just discussed might not be the physical laws of nature.
They might be the programmed parameters of a computational construct. The math of string theory even has error-correcting codes, the exact same codes computer scientists use in web browsers built directly into the equations of supersymmetry.
So the final question isn't just what are the rules? The question is who or what wrote the code?
That completely reframes everything we just talked about. Thank you so much for taking this incredibly deep dive into the source material with us today. Keep looking up, keep asking the hard questions, and never stop questioning the true nature of your reality.